Hello. So let's just have a tutorial session today instead of covering a new topic. So do you have any doubts in all of these topics? Like we have started with regression and then discussed regularization and bias variance trade-off, which will basically explain your underfitting and overfitting concepts. And then you have your base classifier. Right? Do you have any doubts in any of these topics? No. Okay. Yes? Why is it square? See, it's just a standard notation where instead of using your mean squared error, okay, just see bias square, what did I define? I think it is your is this your bias? Is this your bias? Can you cross verify? Is this your bias? Okay, so here instead of using a mean squared error, if we have like RMSE, right? RMSE as your training error. Okay, so then what? See, root of your error square you will have. Okay, so here if you square this, then you will get your MSE. Okay, so your training error, if you are considering it as root mean squared error, then your bias square is equals to your this expression. See, there is no reason, there is nothing more intuitive or logical here. It's just the notation. If you are considering root mean squared as your error, your training error that you have defined, that becomes square of your root mean squared error. So you are using bias square, that's it. Any other doubt? Any other doubt? Okay, so let's solve some questions. Okay, assume that you have a discrete random variable. Okay, maybe let's not get this question. Suppose if you have data distributed like this, where you have class 1 and class 2. So class 1 data points and class 2 data points you have distributed, distribution is like this, okay, your training data distribution. So can you solve this problem using logistic regression? What did we discuss about logistic regression? It was a generalized linear model, right? It is in a way using linear plus your sigmoid or softmax. So now given this distribution, can you solve this problem using logistic regression? If yes, how are you going to solve? So did we discuss any non-linear regression in our classes? Have you seen any non-linear regression? Polynomial, right? Where you have like non-linear relationship between your input and output. So instead of just using your simple linear, what you will do, you will just transform your data with higher order terms. Instead of just considering x, you can consider x square, x cube and x power 4, the higher order terms, and then you can fit a regression model on that. So now in this case also, your data is non-linearly distributed, and if you want to still solve using logistic regression, then the solution is to transform your data, right? Using your polynomial, like you can use data points with higher orders. Is this fine? See, kindly don't talk. I'll not be taking attendance. If you are not interested, kindly don't come. But coming to the class and if you make noise, it distracts me so much. Kindly don't do that. Okay, so here, this is a nonlinear distributed data, right? So here, this thing, if you want, this kind of setting, if you still want to solve using logistic regression, you can go for higher order terms and fit a model. Do you think it works in your, like instead of directly using logistic regression will consider a matrix like this, no, x1, x2, like this, and then apply a sigmoid on top of that. So instead of using a simple linear here, if I make use of maybe w2, x2, and with higher order terms as well. Okay, so then it may fix this issue, right? So now we have seen a logistic regression case where you have a simple linear model plus sigmoid or softmax. Now the question is, can we apply regularization to our logistic regression? See, regularization purpose is what? To control your complexity or to basically make your model generalize better, right? So that is the main aim of your regularization. And so the linear model, linear regression plus regularization we have seen. Okay, so this thing we have seen already. So now I'm asking logistic regression plus regularization. Can we do this? Is it possible? See, regularization is what? What is the purpose of regularization? It is basically controlling the complexity, and it is controlling by imposing this kind of norms, right? An L2 norm or L1 norm. Okay, so to your main loss function. To your main loss function, you have L2 norm penalty or L1 norm penalty, and then you will be training your model with the additional regularization term. Okay, so you can do your regularization or you can apply your regularization for your logistic regression also. Can you try and derive what will be your gradients if we have regularization term for our logistic regression? Logistic regression is what? Okay, maybe it's a tutorial, so I don't have to write. So you go back to your notes and write down the loss function for logistic regression. Logistic regression loss function is nothing but your log likelihood or negative log likelihood. Negative log likelihood is nothing but your cross entropy plus your this regularization. Okay, so can you add the regularization and try to derive your gradients? Maybe I'll give you 5 minutes, you have to solve. You can open your notes and see what is the expression for log likelihood. Okay, and what was the derivative that you got? Maybe with a simple case you take. Okay, simple, this case you take. So you got an expression for your gradient. Now I'm asking, with this extra L2 norm term, what will be the gradient value or what will be the gradient? Without deriving, can you actually infer and guess what is the gradient? What might be the gradient? Just go back to your notes and check the gradient expression for your logistic regression, and with this additional term, how will it, like what is the modification? Yes.
Now we were using the regularization term on the non-linear regression,
Yeah.
non-linear regression.
Yes.
We were not using it on a linear regression.
Yes.
So like, in this logistic, the boundaries are linear. So would there be, but like, why are we using regularization in logistic regression? I can't.
Why are we using?
Yes, ma'am.
Oh, that's a great doubt. Okay, I'll tell you. See, suppose if you have distribution like this, okay? Okay, these are two classes. Fine. So for these two classes of data, like there are multiple linear models possible. All of these are possible linear models for this given data set. All of these hyperplanes are possible for this particular data set. Then if I ask you which one is very sensitive and which one is more robust out of all of these possibilities, which one is more sensitive and which one is more robust? See, with your logistic regression, using this data, now tell me, maybe first let me ask you this question. Using your logistic regression, if I start fitting the logistic regression model for this data, my, I am claiming that all of these are possible using your logistic regression. Do you agree with that? Do you think logistic regression will have a unique solution or multiple possibilities? Logistic regression, when you perform on this data, will you be having multiple possibilities or a single hyperplane? Single hyperplane? Okay. Then, any other answer? See, logistic regression, how will we solve? Do we have a closed form solution or are we using gradient descent? What are we using? Gradient descent. When you use gradient descent, there are a lot of random things. First random thing is initialization. Yes. So based on your initialization, your solution will change. Okay, so all of these are possible in your logistic regression. But which one is better out of all of this? This is more sensitive, no? Can I say that? This hyperplane is more sensitive. Right? If it moves slightly this side, then it actually gets into errors. Okay, and when the new test data points, if it is like slightly lying here, yeah, maybe this side here, it will actually classify this as this class, right? So this hyperplane is more sensitive, meaning it is not more robust. Okay, so this is not an optimal hyperplane. See, what I am saying, logistic regression, if you run on this data, you will definitely have multiple solutions. Because it's an iterative algorithm, you are not deriving a unique solution in your logistic regression. You are using gradient descent. So based on the initialization, okay, it will change, right? All of these are the possibilities now. Okay, so now out of this you have to actually get an optimal model. Not the one which is very sensitive, like not the one which actually doesn't generalize better. Now you understand the need for regularization in logistic regression? Fine. You need, even if you are using nonlinearity, you need regularization to perform better on the test data. Yes.
How is regularization forcing us to pick the optimal one? Like, how is it reducing the magnitude of giving us the most best?
See, here in this case it deals with the shift. Okay, but in general, regularization will do what? It will control my hyperparameters, right? A balanced hyperparameter set it will give. So that in turn may give a optimal hyperplane. So if you ask me how is it explicitly shifting, I don't have an answer.
But it still isn't it more dependent on the initialization point?
Yes, it depends. It still depends on, even if you have regularization, it still depends on the initialization. So that's the what drawback of your gradient descent itself, right? You have seen that gradient descent, if you have multiple local minimas, it can end up reaching to one local minima, right? So now, see, now we understood that logistic regression have multiple possibilities, and you also need regularization in logistic regression. Now can you tell me the gradient expression? Just go and see your gradient descent, gradient expression for your previous case. Then you tell me the modified one when we added regularization. Do you have notes with you, the previous notes? It's done? You have derived? Now can you tell me then? Suppose if you have log of L of W, what is the modified gradient for L2 norm? You want to try? No? You want to tell? Yes. So in the previous case, I got something like this, no? Something like this. In the previous case, for my W1, this is what I got. Yes? As a gradient. Now what will be the gradient?
Ma'am, in the log likelihood, the regularization term would be in the log or outside the log?
In the log? No. See, oh, that's a great question. So, okay, you don't start with imposing the regularization. You have your cross entropy loss, then plus the regularization you add. That will simplify the problem. What? Yes. So once you apply your log likelihood, no? So this your like negative log likelihood you have. So this was the previous loss function, and now you add this, that's it. For the previous loss function, just add your extra regularizer, that's it. So ideally it should give something like this. Something like this, no? Maybe into 2. Something like this, the extra term you will get. Is this fine? Yeah. L2 norm maximizing, see, okay. So again you have to deal with the signs. Okay, so if you are actually, in this case, in this negative log likelihood case, it is a minimization framework. So I am directly adding my L2 norm and I am minimizing. If you are in the maximization framework, you have to add minus of L2 norm. Okay, so now when you have this, it will actually reflect as the second term in your gradient, right? Okay, so till now we have seen, is this clear? Clear? Oh, yeah. Last part. See, what I am saying, when I am actually adding regularization, my logistic regression formulation, if I actually see my formulation, it boils down to minimizing my negative log likelihood. To this, I am adding one more extra term to minimize my L2 norm. Minimizing L2 norm is nothing but L2 norm regularization. This term I am adding, okay. So then if I actually derive gradient for this entire expression, you will have the previous one as it is. Okay, maybe minus, let's say, pi into xi. This is coming from your previous nodes. Okay, so then you will have this is into 2w1 something, L2 norm. No, if you just derive, it is 2w1. So you are getting this extra term. Now you can actually train your logistic regression model also with this regularization using these gradient expressions. Fine. Fine. So now question number 2. See, if you go back to your linear regression, maybe this question is very simple for you. So we said that whenever there is collinearity, or whenever there is linear dependency in the data, your optimal solution or this kind of solution, no, closed form solution doesn't exist, right? That's what we have discussed. Now what happens to my gradient descent solution? Suppose the data is having some linear dependencies. Okay, so whenever the data is having linear dependencies, your closed form solution won't exist. Okay, because this inverse won't exist and your closed form solution won't exist. Then what happens to your gradient descent solution? Can you comment on this? Maybe in just a single sentence you can comment on the solution given by gradient descent when you have linear dependencies in the data. What happens? Okay, maybe I'll give you 5 minutes. You think for 3 minutes. If you don't find the answer, go back to your ChatGPT and ask, and then you explain. Whenever there is collinearity or whenever there is linear dependency, you are sure that your closed form solution won't exist. That is sure. We didn't say anything about gradient descent. You can still solve your gradient descent, right? But I am asking, can you comment on the solution given by gradient descent? So whenever there are linear dependencies, can I say unique solution won't exist? Unique solution won't exist. If unique solution won't exist, then you will have multiple solutions, multiple local minimas. Then your gradient descent will actually give you one of the local minima, right? Yes. Suppose if you have, just imagine you have x1 and x2 as your data points and y as your label. Okay, so this is your x and this is your 2x. And then you have this y is nothing but x1 plus x2. Okay, so in this case, yeah, so your w1 basically corresponds to x1 feature and w2 corresponds to x2 feature, and then it has to satisfy this y, right? So ideally, yeah, so maybe w1, suppose just take one data point, 1 2 and 2 4 3 6. Okay, so these are the data points, and then you have your corresponding y, 6 and 9. Now can you tell me the possible w1 and w2s? What? 3 0. Possible w1 and w2 if I am fitting a linear regression for this data. 0, 1.5. Is this fine? Okay. Then what are the others? 1, 1. Any other? Any other solutions? 2, 2 comma 0.5. Okay. Okay. So what did I do? I just took some data points which are having linear dependencies and I have my label. So because I have linear dependencies, you have multiple solutions possible. Because of that, your closed form solution doesn't exist. And if you use gradient descent, you will end up reaching one of this possibility. Right? Fine. The question and the answer is clear. So the answer is, like, if you are using gradient descent on this kind of data, you will end up reaching to one local minima point. That's it. Is this clear? Are you writing down or are you looking at your phones? You don't want class on Friday? No? Okay, so this question and answer is fine? Fine. So now one more question. Yeah, so what I'm saying is, adding noise or adding Gaussian noise to the training data points. Okay, suppose training inputs, okay, training input X is equivalent to regularizing your model. Okay, so till now, whenever I said regularization, you have seen only two methods, no? L1 norm regularization and L2 norm regularization. Now I am telling you, suppose if we add, given some training data points, adding Gaussian noise to your Xi is equivalent to regularizing your model. Okay, have you seen this anywhere? Using noise as a regularizer. Have you seen this in your previous courses? No. Okay, so now let's try to prove this actually. Suppose if you have a linear regression model which you are fitting on particular data points. Okay, then if you add some noise to it, see, this is what, maybe if you have your intercept and all, this is nothing but J2 D Wj into Xij. This is your linear regression model. Now you have W0 plus I is equals to 1 to D Wj. Maybe this I am calling it as Xi hat, which is the data point you are getting after adding the noise. Okay, so now I am saying the second model, you have the first one and the second one, no? Second one is like training the first model with regularization is equivalent to training your second model. Okay, so adding noise is one way of regularizing your model. Okay, fine. So shall we start proving it? Yes. Standard Gaussian. Yeah, standard Gaussian maybe with you assume zero mean and a variance. Okay. Why not? Why not unit variant? It's up to you. You can assume anything or you can assume some sigma square. So this we have to prove. Okay. Can you try? Just write down the loss function for the second case and try to expand. Yeah. Can you expand these expressions? I won't be solving. I want you to try this. Just in your x hat, substitute xi plus epsilon I and then expand your mean squared error. What?
Regardless of the proof, theoretically, can we think of it like to not get it over specialized on the training data we are?
Yes, that's great. Yes, yes, yes. Don't be too sensitive to the training data points. Add some variations, then train your data. That itself will regularize your model.
Will not that the noise that we are adding to that would and trending numbers will be honest.
What?
The trends that the data is exhibiting, what it get displaced.
Yes, that depends on the amount of noise you are adding. The same way, the amount of regularization you are doing. If you too much regularize your model, in your traditional regularization, maybe I will try to write down the result. Okay, you have to go back and prove it. Okay, yeah.
Like if some feature has a large value, so
Yes.
this noise would shift that feature to
But that depends on the amount of noise you add. Okay, suppose without noise case, okay, without noise case regularization, let's see. Okay, so let me write down the results right now. Okay, you go back and prove. I will anyway share the solution. You have to read by yourself. So suppose if you have this lambda is controlling your amount of regularization, and in this case actually this is equivalent to L of plus your sigma square into your amount of noise will control the amount of regularization here. So like you are saying, if I add noise, okay, if I add too much noise, then again, even in your traditional regularization with L2 norm, if your lambda is too high, you are again going in the wrong direction, right? Here also the same. The amount of noise will actually decide the amount of regularization that you are doing. Fine. So this proof is actually very easy to follow. So that anyway I'll share the notes. But I just wanted you to know that there is one more regularization method also, that is just by using noise to your input data points. Okay. Just by adding some Gaussian noise to your input data points, you can regularize your model. Okay. Maybe those who have done deep learning might know this. Okay, so this result you want to try now? So, one more question. Yes. Okay. Yes. You have your data which is already Gaussian, and then you are adding some noise to it. See, this this Gaussian noise that I am adding, the purpose is to not to make my model specialized on my training data points. Okay, just that X. So I am considering small variations and then I am trying to fit my model. Right? So suppose if you have, like you have these data points with you. Okay, so these are the data points and then you are adding small noise and then you are using those data points to fit your model. Okay, so in your question, no, you are saying the data itself is coming from a Gaussian and then I am adding some more a Gaussian. See, it's again the same purpose actually here. Mean and variance are different, yeah. In that case, it can help. If the variance of your noise is too small, it should not be comparable with your original data set. If you are adding noise which is comparable to your original data set, you are completely shifting your data points. So now what happens, the last question, what happens to your Bayes classifier in presence of outliers? Is it robust or will it get impacted? Can you think and tell me? What happens to your Bayes classifier in presence of outliers? Suppose you have some data points, okay? Maybe some like this, like distributed at this point more, and then you have some more data points here. Okay, so now what will, maybe suppose if I don't have this in the first phase, then a simple Gaussian this way will fit. If I have my data distributed like this, so this Gaussian will fit these points, assuming that my data points are centered here, like accumulated more here. So now if I have some more outliers, I added some more outliers into my data set. Now what happens to my Gaussian fit? It will be skewed, right? It may come like this. Why will we get like this? Because you have mu and your sigma. Your sigma should accommodate your outliers also, right? So your sigma value will basically change to accommodate your outliers also. Then your Gaussian fit will shift. So now can you say your Bayes classifier is robust to outliers? Or it's not robust to outliers? It's not robust. Okay. So there is a model. So here you can see, so this Gaussian is your, this green color one is your Gaussian, and when you have outliers like this is your like main data set and these are outliers, your Gaussian fit will shift. But there is one more distribution that is called student's T distribution, that is not actually not, it is not impacted by your outliers. Okay, but in general we use Gaussian because of the simplicity and because of the real world data sets nature. We will use Gaussian, but Gaussian fit will be impacted if you have outliers in your data. Fine, so one more last question we'll do. Suppose if you have a distribution with 0, 1, 2, 3, 2 theta by 3 and theta by 3, 2 into 1 minus theta by 3 minus 3 by 3. Okay, so if you have a discrete random variable x and it is defined using a parameter theta, and you have 10 observations with you, okay, so n is equals to 10, capital N is equals to 10, you have 10 observations. So out of these observations, these are the observations, okay, 3, 0, 2, 1, 3, 2, 1, 0, 2, 1. How many you have? 1, 2, 3, 4, 5, 5. So now can you actually can you do that? Just find out optimal theta using this observations and the discrete random variable. How will you do? Write down your likelihood for the observed data points. Those are 10 data points. And then you have to maximize your likelihood with respect to theta and derive theta. Please write down and do it. Just write down the likelihood for your 10 data points, and then that likelihood will be in terms of your theta. You have to maximize that with respect to theta and find out the optimal theta value. 0.5? You got it? Okay. Yes, 0.5. Maybe this is too simple for a JEE aspirant. Okay. So you want any difficult questions in the exams? No? Okay, then any more questions? No. Fine, then you can have, see, I won't be here on next Friday. So, but you have to come and practice, okay? TS will be coming and you can have a tutorial session. And next 2 classes we'll have next week. Thank you.